Hey guys, this is Miss Bufford, and in this video, we're going to talk about empirical and molecular formulas. So your learning goals for this video are to be able to differentiate between empirical and molecular formulas, to be able to calculate the empirical formula from mass percent data, and to be able to calculate the molecular formulas from molar mass and empirical formula. All right, so the first thing that we're going to talk about is the difference between the molecular formulas and empirical formulas. And so a molecular formula represents all of the atoms that are present in one molecule or one formula unit of a compound. And we call this the true formula. The empirical formula represents only that smallest whole number ratio of those atoms in that compound. This is the simplest form of a formula. And really, if the empirical formula is different than the molecular formula, then all it's really telling us is the types of elements involved and what ratio they are combining in, right? And so we've heard this term smallest whole number ratio before. And we've heard that term when we talked about ionic formulas. All ionic compounds, when we write their formulas, they're all empirical formulas because they're always written in the smallest whole number ratio of atoms that need to combine to make the smallest recognizable unit of that substance. But when we're talking about covalently bonded substances, things that actually form independent molecules, rather than that repeating structure of positive and negative charges like ionic compounds, we need to find a way to determine the ratio of atoms in these molecules. And that's where the empirical formula comes in handy. So the next question that we want to ask is, why do we need knowledge of empirical formulas? Why do we need to know why do we need to know this? And one answer to that question is that often, either in experimental settings or even sometimes in like forensic settings, we need to be able to identify substances. And so the way that they do that, a forensic scientist would collect a sample of an unknown substance and then take it back to the lab, and they would perform some experiments, run some tests on that sample in order to determine what elements that compound is made of. And once they're able to do that, they can quantify those particles. They can determine what percentage of that sample is made of these different elements, and then eventually determine what the ratio of those atoms in that compound is. And then through another test that they can perform to determine the molar mass, they can use the molar mass and that new empirical formula that they've determined to determine what the molecular formula is. And in doing so, they're identifying that substance. And so the calculations that we're about to learn are things that are really actually used in forensic labs to identify unknown substances. All right, and so what I've done on this slide, the first thing that we're going to talk about here is how to calculate the empirical formula when we're given the mass percent data. And I've listed some steps, but I think it's going to be a better approach for me to just do an example and explain it to you while I'm doing it. But then you also know that later when you go to perform these calculations on your own, that you do have this list of steps here that you can use to help walk you through that problem. So just keep in mind that you have these steps in this video and in the PowerPoint that accompanies this video. So our first example says that the percent composition of a compound was found to be 63.5% silver. So I'm going to go ahead and underline all of the information that's being given to me. 8.2% nitrogen and 28.3% oxygen. And what I need to do is I need to take that information that's given to me and put it into a list. All right, so I'm going to go ahead and start listing out my different elements and the information I have about each one. So my first element I have is silver, and I know that the sample that I have is 63.5% silver. And then I have nitrogen, and the nitrogen sample I have is 8.2% nitrogen. And then for oxygen, my sample is 28.3% oxygen. All right. So when we're trying to determine the empirical formula for a substance, what we're really doing, remember, is we're trying to determine the ratio of these different atoms in this compound. And in order to be able to determine the ratio, I have to have some way of knowing how many atoms of each element I have, because I have to know how many I have if I want to put those numbers together to determine what ratio they're combining in. So I'm being given percentage data, and what I really need is I need to be able to eventually get this to an amount in moles, right? Because remember, moles tells us how many particles we have, and that's our goal here. So I am going to play pretend for a minute, and I'm going to pretend that I have a 100-gram sample of this, that my sample is exactly 100 grams. And if that is the case, so here's my pretend 100-gram sample of this unknown substance. All right, I have a 100-gram sample. If I have 100 grams, then 63.5% of that sample is going to be equal to 63.5 grams of silver. And of that 100-gram sample, 8.2% is going to be nitrogen, which means I have 8.2 grams of nitrogen. And then for oxygen, I'm going to do the same thing. 28.3% of 100 grams is 28.3 grams of oxygen. All right, so now it feels like we're getting somewhere. Now we're in grams, and I know from building block 1 that I can convert grams of any substance to moles of that substance if I use the molar mass. And so let's figure out what we need to do to convert grams to moles. And so I'm just going to bring up our flow chart from building block 1 really quick, just so we can take a look at this and use this to help us figure out where to go. So I have grams, and I'm trying to get all the way over here to moles, and so if I follow the arrow, this is telling me I need to divide by the molar mass. So I'm going to go back to my problem here, and I need to divide each of these by the molar mass for the substance or the element that I'm dealing with in each one. So for example, silver here, I'm going to have to divide this by silver's molar mass, and so I'm going to go to my periodic table here real quick. Let me erase some of these. And silver is right here on our periodic table. I'm going to zoom in just a second, and you'll see that silver's molar mass is 107.868, and I want you to round these to 2 decimal places, remember, so we're going to use 107.87. So 107.87 grams per mole for silver. All right, and because that chart, remember, told me to divide by the molar mass, I'm going to put the mass on the bottom in the denominator. All right, and I'm going to do the same thing for nitrogen. Nitrogen's molar mass is right here. 14.01 is the number that we're going to use for that per mole. And then oxygen is right here, right next to that. So 16.00 is the molar mass that we're going to use for oxygen. All right, so now if I just perform these calculations in my calculator, I have 63.5 divided by 107.87, and I get 0.58, and I'm going to need 3 significant digits, 9 moles of silver. All right, then I'm going to have 8.2 divided by 14.01, and I get 0.59 moles for nitrogen. And then for this last one, 28.3 divided by 16, I get 1.77 moles of oxygen. All right, so now this is great. Now I know exactly how many particles I have. If I know how many moles, then I have a quantity for the number of particles that I have, and I can compare moles of silver to moles of nitrogen and moles of oxygen. because they all represent a quantity or a number of particles. And I want to figure out what ratio these are going to be combining in. And so what I want to do is I want to identify the element that has the smallest mole amount. So this is going to be the element that I have the fewest numbers of particles of. So the one that has the smaller mole number has the fewest particles, which means if I have this in my substance, I'm going to at least have one of these elements, one of these atoms in my formula. And so what I want to do is I want to compare the numbers of the other elements to the one that I have the fewest of. So I'm going to go ahead and choose the number here for silver because I have, the least amount of silver. So I'm going to divide all of my mole amounts by the amount for silver. 0.589 and then 0.589. And what this is going to tell me is it's going to tell me so this tells me right here that I've got one silver atom. All right. This one right here tells me that I have one nitrogen atom. Right. And then if I divide 0.77 divided by 0.589, then that tells me I have 3 oxygens. And so if I were to write the formula for this, I would have AgNO3, 1 silver, 1 nitrogen, and 3 oxygens. And so this here would be my empirical formula. All right, so that is how we calculate the empirical formula. Remember, this is the most simplified version of these formulas. All right, so we're going to go ahead and do one more example. And I wanted to do this example because I wanted to point out that in this particular problem, and then there are some others like this in your practice packet, where you have to do a little bit of an extra step at the end in order to get to your final empirical formula. So let's go ahead and read through the problem. I have a 170.0 gram sample of an unidentified compound that contains 29.84 grams of sodium. So there's one piece of information. Then I have 67.49 grams of chromium, and then 72.67 grams of oxygen. And it's asking me again to calculate the empirical formula. And so I'm going to start by listing out my elements and all of the information I have. So I have sodium, and that has 29.84. I have 29.84 grams of sodium. And then for chromium, I have 67.49 grams for that. And then oxygen, I have 72.67 grams of oxygen. All right, so because I've already been given an amount for each element, I don't have to do anything with percentages. I don't have to pretend I have 100 grams. I'm already in grams. And so all I need to do is convert grams to moles at this point. And remember, we do that here by dividing the mass by the molar mass. So I have the molar mass for sodium is right here, 22.99. 22.99 grams per 1 mole. The molar mass for chromium is right here. That's going to end up being 52.00 grams per mole. And then oxygen is, we take a look at our periodic table, we've already seen this one, but it is going to be 16.00 grams per mole. All right. So now I just need to perform these calculations. So 29.84 divided by 22.99, that's going to equal 1.298 moles of sodium. And then 67.49 divided by 52, that's going to equal 1.298 moles of chromium. And then this last one, 72.67 divided by 16. And that is going to equal 4.54 0.2 moles of oxygen. All right, so now I'm at the step where everything is in moles. So now I need to choose the smallest mole amount, which these are the same, so I'm just going to pick one, 1.298. And I'm going to divide these all by the smallest mole amount, 1.298, and then 1.298. Make that red too. All right, so then if I do this, I have 1 mole of sodium, I have 1 mole of chromium, and then I have 4.52 or 4.542 divided by 1.298, and that equals 3.5 moles of oxygen. And so when you get a decimal number, anything that is less than 0.8 or greater than 0.1, you do not want to round. All right, you don't want to round these numbers because if you end up rounding, then you're going to end up with the wrong ratio of atoms in your formula. And so I'm going to go ahead and I'm just going to write my formula up here just as it is. I have 1 sodium, 1 chromium, and 3.5 oxygen. So I can't leave the decimal there, but I definitely don't want to round. And so what I want to do is I want to multiply all of the subscripts in this empirical formula by something that is going to get me to a whole number for that oxygen. And in this case, because I have a 0.5, if I multiply all of these subscripts in this formula by 2, then I end up with Na2Cr2O7, and that gets me to that whole number. And here is my, this is my empirical formula. Now I'm going to go ahead and I'm going to put some numbers up here. These are numbers that you want to hang on to, so maybe put them in your notes. But these are all going to help you figure out what to multiply these by when you get different decimals. So just like we did just now with 0.5, you want to multiply those times 2. If you have a number that is 0.3 or 0.6, you want to multiply those by 3. If you have a 0.25 or a 0.75, then you multiply those by 4. And then if you have a 0.2 or a 0.8, you want to multiply those by 5. All right, anything that is not going to round to a 0.2 or a 0.8, and let's say it's going to be like a 0.1 something or a 0.9 something, and it's not going to round to either one of those numbers, then you can just round that up to the nearest whole number. But if it ends with anything near what you see here in this chart, you want to make sure you're using these multipliers to multiply all of the subscripts in that formula. All right, so remember that this is a list of important numbers to have. All right, so let's go ahead and we're going to move on to calculating the molecular formulas. And so now that we know how to calculate empirical formulas, we can talk about molecular formulas, because we are going to need an empirical formula and the molar mass, the true molar mass of the molecular formula in order to calculate this. And so just like I did before, I have this list of steps here, but it's not going to be very meaningful unless you can see them in an example. And then after you see the example and you've learned how to do the calculation, you can refer back to this slide to use those steps if you need them. All right, so let's go ahead and do our first example here. This problem says determine the molecular formula for a compound with an empirical formula of NH2 and a formula mass or true molar mass of 32.06. So we've got two pieces of important information here. One is our empirical formula. Remember, that's the simplified version. And then we've got the formula mass, or we sometimes can hear this called the true molar mass of 32.06 atomic mass units. And what this is the actual mass of one molecule of the substance in question. Okay, So this is not the mass of the simplified formula. In order to determine how many times larger this mass is from this, then I need to first calculate something called the empirical mass. And the empirical mass is basically just the molar mass of the empirical formula. So here's my empirical formula, NH2. I need the empirical mass. So the empirical mass is just the mass of this compound. And I just calculate it just like I would calculate a molar mass. I'm going to list out my elements. I'm going to count them. I have 2 hydrogens. I'm going to multiply by their molar masses. And then I'm going to add their molar masses together. All right, so this is my empirical mass right here. I've calculated my empirical mass. That is the mass of this empirical formula. All right, and what I would like to do, or what I need to do, is I need to use this in a formula where I can determine how many times larger my actual molecule is. So I'm just going to go ahead and write out the formula here for you. I'm going to have the true molar mass, and I'm going to divide that by the empirical mass. And that is going to tell me how many times larger the molecular formula is. Okay, so if I do that, let's say I'm going to take my true molar mass, 32.06, and I'm going to divide it by my empirical mass, 16.03, and I can see very clearly with my eyes without using the calculator that that is going to be equal to 2. And so you should get a whole number for this. And so what you want to do is you want to take your empirical formula, NH2, and you want to multiply every subscript in there by 2 in order to come up with your molecular formula. So my molecular formula in this case will be N2H4. All right, so that is how we calculate the molecular formula. We just determine how many times larger it is by calculating the empirical mass and then dividing the true molar mass by the empirical mass. And then we just multiply all of the subscripts in our empirical formula by, how many times larger that molecular formula ends up being. Okay? So let's go ahead and put all of the steps that we've learned for calculating the empirical formula and the molecular formula together. So we're going to put it all together in one big last problem. All right. So in this problem, it says a 3.585 gram sample of an unknown substance contains 1.388 grams of carbon. So there's my first bit of information. 0.345 grams of hydrogen and 1.850 grams of oxygen. If its true molar mass is 62.00 grams per mole, what is the molecular formula? All right, so the ultimate goal here is to determine what the molecular formula of this substance is. But in order to do that, I also have to know what the empirical formula is. And that is not given to me here, but it gives me the data to be able to calculate the empirical formula. And so I'm going to go ahead and start by, again, listing out my elements. So I have carbon, which is, I've got 1.388 grams of carbon. And then hydrogen, I have 0.345 grams of hydrogen. And then for oxygen, I've got 1.850 grams of oxygen. And since these are all given to me in masses already, all I have to do is convert them to moles using the molar mass. So again, for carbon, carbon's molar mass, if we take a look at the periodic table, is going to be 12.01 grams per mole. Hydrogen's molar mass is 1.01 grams per mole. And then oxygen's molar mass is 16.00 grams per mole. All right, so now I'm going to go ahead and perform these calculations. 1.388 divided by 12.01, and I get 0.1156 moles of carbon, and then 0.345 divided by 1.01 moles, so I get 0.342 moles of hydrogen. And the last one, 1.850 divided by 16.00 equals 0.1156 moles of oxygen. And so my empirical formula here is going to be determined by dividing these by the smallest mole amount. Almost forgot that step, don't forget it. 0.1156 is my smallest mole amount, so I'm going to divide all of these mole amounts by that amount. Okay, so if I do that, I have 1 mole of carbon, I have 1 mole of oxygen, and then 0.342 divided by 0.1156. That means I've got 3 moles of hydrogen. So my empirical formula now is CH3O. Okay, so there's my empirical formula. But remember, the problem's asking me to find the molecular formula. But I do need the empirical formula in order to do that. And so now I have what I need to calculate the molecular formula, which is the empirical formula and the true molar mass, which is right here, 62.00 grams per mole. So in order to be able to divide my true molar mass, which is 62.00 grams per mole, by my empirical mass, I have to first calculate my empirical mass. So I'm going to do that over here. I have carbon, hydrogen, and oxygen. 1 carbon, 3 hydrogen, and 1 oxygen. So if I go ahead and do these calculations, 3.03 and 16.00, and I add those numbers up, so 12.01 plus 3.03 plus 16, I end up with a total empirical mass of 31.04 grams per mole. All right, so if I take my empirical mass and I divide that, or I divide my true molar mass by that, so 31.04 per mole, I can see very quickly that that is going to be just about 2. All right, so that means that I'm going to multiply all of these subscripts in my empirical formula by 2. And so I end up with C2H6O2. And this right here is my molecular formula. All right, so I hope this video was helpful. If you guys still have questions, please come see me either during class or during tutorials. Thanks for watching Buffered Chemistry. Subscribe to my YouTube channel for more chemistry help.